And welcome back. As we continue our exploration of our very own sun, we are now going to go ahead and shift our focus to really examine the solar interior in a little more depth by first looking at it from the theoretical angle. So the first thing we have to understand about our star is that our sun is really just a giant blob of plasma. The sun is so hot that all the material in it is in the form of plasma. If you remember, this is ionized gas. And plasma, in turn, acts very much like a hot gas. The particles that constitute a gas are in rapid motion, frequently colliding with one another. Now, this constant bombardment is the pressure of the gas that the sun exerts. More particles within a given volume produce more pressure. And the pressure is also greater when the molecules or atoms are moving faster. Higher temperatures, which as we see in the sun, also produce a higher pressure. Now, the thing to keep in mind is even though the sun is quite large, it is also very stable. The sun, like most other stars that we know of, is stable. It is neither expanding nor is it contracting. Now, such a star is said to be in a condition of equilibrium. All the forces within it are balanced, so that each point within the star, the temperature, the pressure, and the density, and so on, are maintained at constant values. Now, these stable stars, including our very own sun, do change as they evolve over their life, but such evolutionary changes are so gradual that the stars are still in a state of equilibrium at any given time. And so, what does that mean? Well, we have a terminology for this, hydrostatic equilibrium, which means that the mutual gravitational attraction between the masses of various regions within the sun produce tremendous pressure that tends to collapse the sun toward its center. And we know that the sun has been emitting roughly the same amount of energy for billions of years, so clearly it's managed to resist this gravitational collapse for a very long time. Now, the gravitational forces must therefore be counterbalanced by the pressure of the gases within the sun. So as gravity pulls inward, the pressures are pushing outward. If the internal pressure in such a star like our sun were not great enough to balance the weight of its outer parts, the star would actually just collapse, contracting and building up the pressure inside. On the other hand, if that pressure were greater than the weight of the outerlying layers, well, the star would expand, thus decreasing the internal pressure. Expansion then at that point would stop, and equilibrium would again be reached when the pressure at every internal point equaled the weight of the stellar layers above that point. Now, again, the technical term that we have for this balancing act is hydrostatic equilibrium, and all stable stars are in a state of hydrostatic equilibrium. Now, another thing that you might want to think about is the sun is not cooling down. This is a misconception you might have, because usually when we think about hot things, if we leave them out long enough, they will get cool enough where we can then touch them. Well, with the sun, this doesn't happen, because as energy filters outward toward the surface of the star, it has to flow from the inner hotter regions. The temperature cannot get cooler as we go inward, or energy would flow in and heat up the regions until they release as hot as the outer ones. So temperature is always going to be the hottest at the center of a star and dropping to lower and lower values toward the stellar surface. Now, obviously, we can have different things happen, for example, with the atmosphere, like we saw, for example, the sun's corona, the magnetosphere, trapping in that heat, and so we get it quite hot. But in terms of the actual core to surface, generally speaking, the core is going to be the hotter points, and then the surface will be cooler. Now, this outward flow of energy through a star robs it of its internal heat, and the star would cool down if the energy were not somehow replaced. Therefore, a fresh source of energy has to exist within each star. In our own sun case, we have seen that this energy source is the ongoing fusion of the hydrogen to form helium, and that, of course, produce heat. And one of the byproducts of that proton-proton cycle is that we do have two hydrogens that end up at the end, and so those two hydrogens are then able to start the cycle anew. Now, if we start looking at the heat transfer in a star, there's a couple things here to recall. Since the nuclear reactions that generates the sun's energy occur deep within it, the energy has to be transported from the center to the surface in the form of both heat and light. Now, there are three ways in which energy can be transferred from one place to another. We have conduction, where atoms or molecules pass on their energy by colliding with others nearby. We have convection, which are currents of warm material that rise, carrying their energy with them to cool layers. And radiation, where energetic photons move away from hot material and are absorbed by some material to which they then convey some or all their energy. In stars, radiation and convection are very important things, whereas conduction can usually be ignored because we don't really have much form of conduction currents. We do have convection currents within our sun, and we do have radiation that comes out from the core. So let's go ahead and look again at that stellar convection, because we have talked about this a little bit. But just as a reminder that stellar convection occurs as currents of hot gas flow up and down through the star. Now, such currents travel at moderate speeds and don't upset overall stability of the star. All right, it's just part of the natural process. These loops don't even result in a net transfer of mass either inward or outward, because as the hot material is rising toward the surface, cool material is going to fall and replace it. And so this kind of just results in a convective circulation of rising and falling cells. Convection currents carry heat very efficiently outward through a star because, again, you're taking that hot material, you're bringing it to the surface, and the cool material is coming back down. Now, what about the other one we mentioned, radiation? Well, that's going to have us to think about photons that are deep within our own sun. Radiation is not an efficient means of energy transport in stars because gases in stellar interiors are very opaque, as a photon does not go very far before it's absorbed. A photon moving through the dense gases in the solar interior travels only a short distance before it interacts with one of the surrounding atoms. The resulting photon usually has a lower energy after each interaction and may then travel in any random direction. Right? Because again, it's not bound to necessarily ricochet off in the opposite direction. It just goes off randomly. And this is important to keep in mind as we look at the photon and neutrino paths within the sun. Because if we look at these two diagrams, if we look at photons that are generated by fusion reactions, inside the solar interior, they only travel a very short distance, and what happens is that they are either absorbed or scattered by atoms and then sent off into those random directions, as we mentioned. And so it's estimated that the photons of light take anywhere between 100,000 to 1 million years for that energy to make its way out from the center of the sun all the way to the surface. In contrast, neutrinos do not interact with matter. Remember, they're antimatter particles. So they tend to traverse straight through the sun at the speed of light and can reach the surface in a little more than 2 seconds. And so this whole thing is very important when we start talking about modeling our star. Scientists have used those principles we have just described to calculate what we think the sun's interior is like. Now, these physical ideas are often expressed as mathematical equations that are solved to determine the values of things like temperature, pressure, density, the efficiency with which protons are absorbed, and other physical quantities throughout the sun. Now, these solutions obtained provide a theoretical model for the interior of the sun. Now, again, up to this point, everything we've talked about is theoretical, but what can we do to actually add some more concrete evidence to it? Well, this means we're going to need to do some observations of the sun and its interior, which is what we will look at next.